Hi everyone, I'm Zhiming from Louisiana State University.
Hi, I'm Jingyan from Iowa State University. Today, we will present our team's work on Project 3 for condition assessment of state cables. In this project, we detect the most probable damaged cable through enhanced time series classification using a deep learning approach. This is our outline of the presentation today. The topic of Project 3 is a condition assessment of state cables. For a cable state bridge with a total of 168 cable, the cable tension force was measured from 14 cables or 7 cable pairs using installed load cells at a sampling frequency of 2 Hz. Among the 10 days with measured cable forces, all 14 cables were intact on the first 9 days without any damage, but one cable was found to be damaged with wire ruptures inside the cable prior to the last day in the year 2011. So our goal is to find the damaged cable through the measured data.
In this study, we proposed identifying cable damage through time series classification using a deep learning approach. Time series classification has wide applications in many areas. For the cable damage detection problem, the segments of measured data series are taken as the data samples. It can be the time series of cable forces collected from a certain cable or the cable force ratio of a certain cable pair. The labels for this time series classification problem are set as the ID of the cables or cable pairs. With this setup, we expect to learn a time series classifier that maps well from the time series data to their corresponding labels. With this idea, a time series classification model can be learned using the data collected from all cables under intact conditions. When testing the learned model on new data collected from a certain cable, if the tested cable is still intact without any non-trivial damage, then the measured data should be correctly classified using the learned model. In contrast, if the tested cable has been damaged, then the cable's behavior should have transitioned to a different pattern. As a result, the model learned using the intact data cannot generalize well to this damaged case, and the classification accuracy of the new data should be very low. The long short-term memory fully convolutional network model proposed by Quinn in 2017 is used in this study for time series classification because of its advantage in reduced preprocessing compared with other deep learning models. This model mainly consists of the FCN module and the LSTM module. The FCN module contains a 1D convolutional layer for feature extraction and a radio activation function in each block, followed by the global average pooling layer to reduce the model's complexity. The LSTM module is added in this model for feature augmentation and model regularization. The dimension software in this model is expected to reduce the overfitting of the learned model, which is followed by a standard LSTM block. The features extracted from these two modules are concatenated and passed onto the softmax layer that maps the feature vector to the probability of each class. To validate the proposed methodology, an experimental case study is implemented using the data provided in Project 3 for state cable condition assessment. First, the collected data are pre-processed to detect and remove outliers in certain data series and identify the data measured from field sensors. Following that, an LSTM FC model is configured and trained using the data collected from all cables under intact conditions. As mentioned in the methodology section, two scenarios are investigated in this study. The final decisions about the most probable damaged cable is made through combining the testing results in these two scenarios.
In the data pre-processing stage, extreme values in certain data series are taken as outliers and excluded through them from the normal range. For example, here, the cable force data on this sensor has a certain day slow very large small values at some locations. But there is extreme values at the end, so we exclude it from the original data. And after removing the outlier from the pre-processing of the data, we also identify some two sensors that has extremely small magnitude and also small fluctuation. It has the reversal or random drift patterns, which is different from the other sensors that has a periodicity pattern that was introduced by the traffic loads and the temperature effects. So these two sensors has been identified as sensor failure and would be excluded from the classification program. The original data of the cable 4 series we collected from a certain cable on a certain day will be segmented into 108 segments of the length of 1,600 data points. Regarding the data assignment for learning a time series classification model, the intact data prior to 211 is equally divided into training and testing data set, which are used to learn an efficient model for the intact data. Finally, the learned model will be tested on the data collected in 211 for cable damage detection.
The Keras library with the TensorFlow backend is used in this study to build and run the LSTM FC model. Regarding the model parameters, the cell number of the LSTM is set as 8. 3 1D convolutional layers are built in the FC module, with the kernel size set as 128, 256, and 128 respectively. For the model training, 2,000 epochs are run for each simulation with an initial batch size of 128. Adam optimizer is used to tune the model parameters. An adaptive learning rate strategy is adopted. The classification performance is evaluated using the average accuracy of all time series segments belonging to a certain class. These two tables list the classification accuracy for each dataset in the two scenarios. It shows that in scenario 1, when testing the model on the intact data collected prior to 2011, the classification accuracy is nearly 80%. However, the overall accuracy on the data in 2011 is only 56% due to possible damage occurrence. In detail, the classification accuracies are all above 50% except for the cable SAS11 and SAS10 that have an accuracy below 30%, which indicates possible cable damage among these two cables. In scenario 2, with the cable false ratio used at the input data, the classification accuracy on the intact data is increased to 96%. However, the overall accuracy for data in 2011 is only 75%, which again indicates possible damage on a certain cable pair. Among all cable pairs, SA11 had the least accuracy, which is much lower than that of other cable pairs. So which one is the most probable damaged cable? Combining these results in these two scenarios, the most probable damaged cable can be determined as SAS11. This is consistent with the results in this paper, which recommends the most probable damage in cable pair SA11. Compared with that study, we successfully detected not only the most probable damaged cable pair, but also the exact cable. Additionally, we obviated the intensive work for data preprocessing by using an improved deep learning model for time series classification. With this, we would like to present the conclusions of this study.
So this study proposed a cable damage detection method through time series classification using the deep learning framework. Two scenarios were investigated with different input and class labels. Combining these two results, the most probable damaged cable is consistent with the results in the literature. This proposed method enables fast and convenient early detection and warning in the real applications, and more case studies will be conducted in the future network. Our team members is based at 4 universities in the United States, and our team would like to acknowledge the organizing committee of the first international project competition for structural health monitoring for sharing all the materials and the data for this project. And I would like to thank their time and replying our inquiry inquiries every time. Thank you.
Thank you.